uh, the hydrogenic atom, and the last time we have discussed about the magnetic quantum number, and then angular momentum quantum number, and spin quantum number. And today we are going to discuss about the principal quantum number. Okay, the principal quantum number is just quantum number which is related to the energy state. This is the only one which is related to the energy state of the hydrogenic electrons. Okay, so it is the only energy related quantum number, and then of course it is a function of the radius r, the distance. And this quantum number can be, it's a solution of the equation that we have discussed the last time. In the separation of variables, we have three equations, and among those three equations, we can get this equation related to the principal quantum number. Okay, and R and L solution of this is something very complicated equation which is given on the text. Okay, and in this equation, the charge density is going to be 2Rn A naught, and here the A naught is a Bohr radius, is going to be called Bohr radius. And then that is something like this. And the Bohr radius is the radius. This is the radius of a ground state. Ground state of a circular orbit. Okay. And nth, this is a ground state. Ground state of circular orbiting electrons. Nth state is going to be the Rn, the distance between the nucleus and the electron is going to be n square A naught, approximately. Okay, then this A naught is 0.53 angstrom. Of course, here the n is 1, 2, 3, 4. That's a digit. Okay, the spin quantum number is just a plus minus half. Okay. That's just two things. So finally, we can say the psi wave equation for hydrogenic electrons. Okay, it's going to be R and theta L M L and phi M L. It consists of three quantum numbers, three equations actually, and plus we have a spin quantum number which is plus or minus 1/2. So it consists of the four quantum numbers. The energy states of electron is going to be related to the four quantum numbers. Now for the ground state, the energy of the ground state of a Bohr radius, it has been calculated in a text, something like this: 9.1 times 10 to the minus 28 gram, 4.8 times 10 to the 10th, and 2 times 1.0545 times 10 to the minus 27 square, and then this is 2.17 times 10 to the minus 11 erg, and that is 13.5 electron volts. So this is the ground state of hydrogenic atoms, the ground states of electrons. Okay, and then the wave function, which is related to the 100, the ground state, then that is R10R theta 00 theta and phi 0 phi. That is, that can be expressed as a exponential minus R over A naught, something like this. All is in simple calculations, and we are not going to actually drive this. The important thing in this class that we want to notice is that the energy states of hydrogenic electrons, okay, how that is different from other electrons like a particle in a box or the lattice atoms. So the main focus that we are going to discuss is delta En, energy eigenvalues difference, that is En minus E1, that is going to be delta En, and then that is calculated to be 2h bar square 1 over n square minus 1, something like this. Okay? So, in summary, particle in a box. That is the case where the electron is confined in a solid. Like a free electrons. Free electrons in a solid. Okay? In that case, what we have seen is that the energy is proportional to the n square, so that the ground state, and as it goes higher and higher, the energy gap becomes larger and larger as the state goes excited state, like something like this, right? And harmonic oscillator case. Harmonic oscillator case. And this is the case where the atomic wave, right? In that case, the energy is proportional to n, so that it's equally spaced. No matter how high the state has been excited, the gap is going to be always delta E is going to be h bar omega, something like this. That has been found. Now, in this hydrogenic atoms, the electrons confined to the atom itself, okay? Hydrogenic atom. Electron confined to nucleus. Okay? In this case, what we have seen is that the energy now is proportional to reciprocal of n squared. That's amazing. So this means we have a ground state here. We call that the 1s state, or something like that. And then the next available state, the gap is very, very huge. But as it is excited more and more, then the gap becomes very narrow. Okay? So all those three cases are different from state to for the case. And all those kind of energy states can be explained with the Schrödinger equations. Of course, this is not kind of thing that we can picture from the substance, materials. We cannot see them, where we cannot see the energy states or something like this. But the phenomenon, the physical phenomena that happens in the solid can be understood by setting this kind of energy states, existence, by acknowledge of the existence of this energy state in the materials. If we assume that, then the phenomena that happens from the solid can be explained. So that's why we want to postulate the Schrödinger equations, and we want to see the substance in the light of the wave instead of the particle. If you think that the electrons and lattice atoms as a particle, then it is impossible to explain this kind of energy gap and quantum things. So all those things, we start out with the string under tension, right? And then we extend that idea to the lattice atoms, and that was easy because we still can use the Newtonian F equal to ma. And the next thing that we have to apply that wave idea, wave picture, was the light wave. And in light wave, we can directly apply that the thing is string under tension, because in the light we don't have a mass. So F equal to ma, we cannot say that. We cannot put that thing into wave equations. So what we did was we used the Maxwell equation, 1, 2, 3, 4, and then mathematically we manipulate, we massage them, to get the wave equations, which is the second derivative partial differential equations with respect to the x and with respect to the time, right? That is the part. That partial differential equation is just nothing but a wave equation, so we deduce that. Now, for the matter wave, electrons and holes, the matter itself, how can we regard the matter not a particle but a wave? In order to do that, we use the Schrödinger equations, and then we finally set up this four different situations. The electrons confined in a box, or the atom oscillations in the lattice, and the electrons confined in one atom. The next task that we're going to do is a free electron model, the chapter 6. And in this free electron model, what we really try to do is that with this base, now we have to think what's going to happen for the electrons, okay? And then put that electrons or put the atoms together. For example, if you have one sodium atom, okay, then it has a 1 s electrons, okay, and then next it has a 2p, 2s2, 2s2 electrons is going to be orbiting something like this. Okay, and then the next it has a 2p6. We have 1, 2, 3, 4, 5, 6 electrons. 4, 5, 5, 6 electrons is orbiting the sodium nucleus. And at the very end, we have one electron very outside of the sodium atoms, like this. It has a configuration of electrons just like this, okay? And this electron, we call that valence electron. So when the sodium atom is independently, is isolated, is just sitting there, then the electrons all have this different energies, just like this, and each electron has a different 4 quantum numbers that we have discussed, right? Now, what's going to happen if you put sodium atom, 2 sodium atoms in a one solid? Okay. Now, in a solid, how many sodium atoms is going to be? It's about 5 times 10 to the 22 atoms per centimeter cube. But let's just think that what happens if you put the sodium atoms, 2 sodium atoms get closer together. Now, when this electron is going to be overlapped, then this 3s electrons, the energy of 3s electrons, and the 3s electrons confined this sodium atom, when they get put together, then this electron and the sodium atom, this sodium atom's 3s valence electrons cannot have the same energy. And that is going to be called the Pauli exclusion principle. Pauli exclusion principle. When it is separated, it can have the same energies. But when those atoms are put into one system, then those electrons cannot have same 4 quantum numbers. Okay, that is called the Pauli exclusion principle. So according to the Pauli exclusion principle, what's going to happen if you put 5 times the 10 to 22 sodium atoms per cube to form a solid? Then in this solid, how many electrons, valence electrons, is going to have? We have 5 times the 10 to 22 3s electrons per cube. And this 3s electron is no longer confined to one sodium atom. So if you look into the solids in detail, then what's going to happen is that this is what sodium atom is going to look like. Okay, you have sodium atoms in the lattice, something like this. Okay. And if it is a single crystal, then it's going to be arranged in a certain it's a regular fashion, right? And then you're going to have all those 1s, 2ps2, 2s2, 2p6 electrons confined to this, each sodium atoms, but the outermost 3s, the valence electron, is no longer belong to this one specific sodium atom. It's going to be floating around. How many of these electrons going to be in this solid? It's exactly the same number of the sodium ions, because each one has only one electron, something like that. Okay? So we call that, this electron, we call that the free electron. And we do not think it does have, we think the potential energy is 0, only it has the kinetic energies, right? Kinetic energies. And this kinetic energy is going to be p squared and then 2m h bar squared k squared, something like this. It is not really free in two senses. One, it is confined in the solid. Unless this electron overcomes the work function, we call that the work function. The energy is going to be called the work function, which is just the energy necessary to escape the electron into the vacuum out of the solid. We call that the work function. So this is not really free because it is belonging to, confined to a solid, okay? And secondly, this electron has to travel in a periodic potential.